Okay, today's lecture we are going to discuss about how do we do designs using memories. We will also talk about how to incorporate memories as part of a state machine, that is to control the memory using a state machine. We already know how to use the other devices with it, and later when we talk of system design, typically today memory forms a very important component of almost all systems. So it will be clear that how you can use this in an environment which consists of other components apart from memory. When we talk of memories, we typically classify memories into various types. Today of course we are not going to discuss about ROMs, we already have used them in designing combinational circuits. So ROMs are basically read-only memories and they differ apart from, of course all memories differ in terms of the size. But apart from that they also differ in terms of the technology, that is the device, how is the device going to be programmed. So the ROMs differ in terms of mask programmable, the devices which need to be programmed at the mask level and cannot be changed, devices which are available to you in a form, in a raw form, and you can actually put whatever data you want, those are called programmable read-only memories. How do you do this programming? That depends, so let's say if this programming is electrically programmable, then they call it EEPROM. Electrically erasable, not only programming but also the erasing part can be done electrically, then it is electrically erasable PROMs. Then you have UV PROMs which are ultraviolet erasable. So there are a very large number of them and they all have their own typical uses. Even in the case when, let's say something you consider a situation whether it is electrically erasable PROM, they are still fundamentally different from RAMs. You can say that they are no longer read-only memory because you can also erase them and you can rewrite them. Fundamentally the way they differ is in terms of the erasing circuitry required, even sometimes the voltages required, the timing required is not the same as the timing and required for reading. The reading requires much less time, whereas the writing requires much longer time. It is not only that, sometimes the erasing is possible only the complete ROM has to be erased or a complete block of a ROM has to be erased. You cannot individually write into locations just like you can write in case of the RAM. So there are also now of course ROMs called flash ROMs and all, which can be also be erased completely and written one location at a time. But even if you are writing one location at a time, the cycle time required for writing is much larger, and so they are fundamentally different. Their structure is different from the random access memory. So today's lecture is going to talk about how do we use random access memory as part of the design. So if you consider the RAMs, of course ROMs are also random access, but traditionally this name has stuck, so the nomenclature is actually wrong. Both are random access. This should have been called read-write memory, but by convention whenever we call a RAM, when we call something a RAM, it's actually read-write memory. As far as access is concerned, both ROMs and RAMs are random access. But there is a read-write memory and they also come in two major categories. One is called the static RAM or SRAM, another is called the dynamic RAM or DRAM. And there is a fundamental difference in the way these circuits are let's say fabricated, and also their interfaces are also different. So today what I am going to discuss in terms of interface and also the device interface, as also how do we use these devices, are also a typical example. It doesn't mean that all SRAMs, there is such a wide variety of them manufactured by a very large number of vendors, and it's not that all of them will be exactly identical, but a large number of them do follow this convention as far as inter-device signals are concerned. So first let me talk about the static RAM and we talk about the device signals for the static RAM. So the static RAM device signals consists of, you have the address lines, you have the data lines, you have read-write line, and you have chip select line. So you have typically this chip select line is a complemented line and it's called CS bar. Read-write, it's called read-write bar because this particular device reads with 1 and writes with 0, and it's called read-write bar. So now if you consider as a SRAM of a certain size, let us say we call this particular SRAM, let us say has a 16K by 8, that is the size. We already know what will be the number of bits over here. This will be 8 bits wide corresponding to the 8 data lines. This will be 16K corresponds to 14 address lines, and this will be 14 bits wide. So this will be a typical pin device signal that will be apart from supply and ground, which I am not showing. Every device requires supply and ground. So you have this, so what happens is you have to supply the address where you are going to read from or where you are going to write. Basically at a particular time when you do a read or a write is governed by this particular signal. Of course there are devices where there are separate read signal and separate write signal, but very often you have only one signal, which is when it is high it is read and when it is low it is write. Then you have a chip select signal, and this chip select signal determines whether this chip is selected at all or not. And typically the usage of chip select is when you want to increase the address space. This is a device which is only 16K bytes. If you want to have 32K bytes or 64K bytes or even larger, you can decode some of the higher address lines and select one of the devices. It is very similar to the way we have discussed in case of ROM, so I don't have to again discuss this. How do we use the chip select? So in all this discussion today, I will assume that how you can expand this device to make a larger capacity device by decoding some of the address lines. Okay, so what are the issues in using a device? First of all, you should understand that RAMs are typically, at least commonly used RAMs are typically asynchronous devices. There is no clock anywhere. You don't see a clock signal as an input. It's an asynchronous device. All the actions, all the timings that are associated with the RAM are specified in terms of minimum and maximum delay times. So you need to give some spacing between the waveforms. You have to have certain width of the waveforms and so on to ensure that this device functions correctly. And what are these? So let me again show us typical timing waveform. There are a lot more details if you go into the specifics of the design. So here we will only look at very important timings. Some of the others, if you are doing a very, very critical design where you are pushing a device to its limits, then you may have to consider some other timings as well. But in typical usage, what the type of timing that needs to be considered, I am showing over here. So as far as again, if you consider this, so I am concentrating on address line, read write line and data lines. I am ignoring the chip select. I am assuming that chip select is the device is selected during the time the operations is performed. So this is my read cycle. This is the time when I am performing my read, and this is my write cycle. So I have one read and one write cycle over here. I am showing both. So in one cycle I am performing read. Cycle, of course, the notion of cycle is here not as yet not related to the clock because it's an asynchronous device. So you have to have a cycle time. You typically associate a cycle time with a memory. It is the time in which a complete read operation can be completed or a complete write operation can be completed. Typically the cycle time for almost most of the RAM devices is same. That is, the time that is required to complete a read operation or a write operation is the same. And during this period, during the cycle, your address should be stable. That is, of course, address changes over here. This is what is shown, and during this time, let us say my address is A, and let us say here I am reading from a location A and I am writing into a location B, let us say. Now this is the read part, this is the read cycle, and there will always be a specification available for what is the minimum read cycle time. Let us say the minimum read cycle time is specified to be 100 nanoseconds. It means you can do 10 million operations in a second on that ROM and on that RAM. You can write 10 million times. Either you can write the number of reads plus writes that are possible in 1 second will be 10 million if your cycle time is 100 nanoseconds. So now during this read time, of course, the read signal is going to be high because this is a read operation. Now what happens is, once this address is given and read is there, This is the data output. Remember, it's a bidirectional data that I am using over here. This data lines are bidirectional, both the input is supplied on the same lines, output also comes on the same lines. Many RAM devices this is true, but there are some RAM devices where these two could be different. You can have a separate line for output and separate for input. I am considering here. So what happens is, during a certain phase, actually there may be a certain phase when you even have this as tri-stated, but apart from that, the output that comes during the read cycle, there is something called an access time of the RAM. There is a time, there is a very important time, and your cycle time is actually very close to, is larger than this, but this is a time that is the minimal time. So if you say that your access time for the RAM is 60 nanoseconds, what it means is, from the time you supply the address, the time it takes to select the proper location which needs to be read. These are, because after all, if it is 16 kilobyte RAM, you have to do the lot of decoding to get to the actual cell on which the data is stored, and that is the time that is related to the T access time. And during this time, your output is not really defined. You could be reading any location because decoding is still going on. The chip select signal and ending of the chip select and the decoding is to travel to the actual cell from which the data has to come, and during this time you cannot trust the output. It may happen that your T axis is specified to be 60 nanoseconds, and sometimes you are actually getting an output at 40. This is the maximum specification, it is not a minimum specification. That means when I say that I have a RAM device which has an access time of 60 nanoseconds, in 60 nanoseconds the output will appear. It can appear of course earlier, it can even appear after 3 nanoseconds. There could be a lot of variation. So during this period I cannot trust the output, but after this, after I left 60 nanoseconds, after the address has changed, I am sure that my output is corresponds to the address that I am reading. The operation that I am performing here is data is going to get from the RAM location A. This is the operation that I am performing over here. And this address should be stable, and if I am going to use this RAM output to latch this into some register, I should do it during this period. During this phase I can, because once the output is stable which corresponds to this particular location, I can latch anywhere during this time, or I can, if I am using an H2 register, I can store this value into this, and then I don't care what happens over here because I already stored the value corresponding to this data. Now let's look at the write cycle. Again, there is a write cycle time which is specified. As I said, typically this write cycle time and read cycle time both are equal, and that's called the memory cycle time. Now let's look at the write signal itself. This is a critical part of the design, and this is what is write signal. What is required is, write signal should be completely encompassed by both the address and the data line. Unlike the case of a read could have been stable here, like this signal could have been read even before and later. But this particular edge, so whatever time your data stabilizes, let's say my data stabilizes here and my address stabilizes here, this particular edge, because it is going to write during this low period, during this edge should follow the stabilization of this. Similarly, it should be stable till the time this edge has come. That is, during the whole time when your write signal is active, it is low, your address and data should not change. This requirement is not there for the read, but this is a very, very stringent requirement for write. Of course, how much distance that should be there, how much timing distance should be there could vary from device to device, but almost all devices require that. This is, if you recollect, this particular time is more like the whole time. I removed the write if you consider the equivalence to the shift register. After all, there are some latches inside. Okay, so when you talk of a RAM device, each cell is like a latch, is like a flip-flop, and it's going to store the data. So the data should remain stable at the time when you are, okay. And typically most RAM devices are not edge trigger devices. They are the flip-flop that are there are level trigger devices. and you essentially specify a minimum period for this. This is the T write pulse, what is the minimum width that is required for this. So during this time, so this is like the setup time and this is like the hold time as far as the data edges are concerned. And of course I don't want this particular data should be written into any other location, so I want to make sure that your address lines come even before this. So the address should come before these edges and the data should also be stable before these edges. A typical sequence is first the address will come, then the data will come, then the write pulse will come, then write pulse will be removed and address and data may be removed simultaneously. This is a typical sequence, and this sequence has to be generated by any device which wants to use this, or in any circuit where you want to use a RAM, you have to make sure that these timing relations are valid. And it's clear that why you cannot have the right to be going when the address is still changing, because you do not want to, unlike a read, no, it's not an operation which is, it doesn't matter if you are reading a wrong location for a certain period of time, as long as you are not latching that. As long as you do not consider that to be the data of address A, it doesn't matter you are reading some A dash location. But you cannot afford to do that. The data that you want to write has to go and update only the location B. It should not update some other location. So there is a very critical requirement as far as writing is concerned. The operation that we are going to achieve here is RAM B gets data. Here my data lines are both same. So any design that you do using RAMs, you have to ensure these timings, and that is critical for your RAM to function properly. Hold time, how much hold time is there? Sometimes some devices are generated with zero hold time, which means that this can actually occur together, but they should not occur, they should never occur later. That's what a zero hold time means. But you may have a requirement of a small hold time and a setup time over here, and you have to ensure that. So this is your data, and this is also your data. So this is how the timing looks like in case of a RAM device. Yes. Okay, for the read part, the address comes and you are in the read mode. So some data will start coming immediately because you are always going to be enabling some location onto the output. I am assuming that the chip select is active. That is, if CS bar is there, it is 0. If chip select is not there, you will have an output which is tri-stated output. We know that if chip select tri-states the output, so you will have a high impedance. But assuming the chip select is going to be there, some data is going to appear at the output, but only after the access time you can be sure that the data that appears corresponds to the location that you are reading. This dashed line essentially means it's an data which we do not know what it is. It's not a defined data. Of course, this stabilization process has to finish by T access time. You have to get the proper data by T access. That is the meaning of T access. For some locations, and also it depends upon what was the previous location, how the chip select, how is the decoding being done and so on. This could come earlier than that. But this T access ensures that by after T access the data corresponds to the location that you are trying to read. That is the important time. So does that answer that question? Yes. Okay. So now let us look at how does the circuit look like where this RAM is embedded. The circuit looks somewhat like this. I have put two registers here, RO, RI, and there is an address. Let me talk of a little bit of a variation here, because this all will be useful for your design, not only design as far as theory is concerned, also in your lab. So when you talk of a RAM, there is of course there is some size to it. I have not shown the chip select here, but there should also be a chip select. Please remember, again I will repeat, that this RAM is an asynchronous device. There is a clock going to all the registers. Same clock. We are now right now considering, let us say it's a single phase clock. The same clock is going to all the registers, but there is no clock going to this RAM. Okay, so that's okay. Now let us. So there is a data bus over here. I am talking again of RAM where. Okay, I should have shown like this. So it reads data, it also writes data through this, but I have registers here to separate out. So data that comes from here goes to this register output, the data that has to go in comes from this register input. And once I make the data bus, I can have multiple sources and multiple destinations, implying that I need not just take the data from just one register, I may have 5 registers, I may have any number of devices. In any particular write cycle, I have to define or I have to decide which particular device is supplying the data. And that can be done through one of the output enable bus, implying that only one of these registers will be enabled. The register that will be enabled will be the one which will be supplying data to the RAM. And this particular register, when you say the register is in the most generic sense, it could be anywhere, anything else, it could even be switches, it could be anything that is supplying data to this. Similarly, when you are writing data into the register, I can have not just have one register, but I can have multiple registers, and I can decide which register is being loaded. I will enable only one of the loads for the registers. Of course, I can also enable multiple registers if I want to copy the same data onto this, because after all this bus is going to all the inputs of all the registers. So this is how my output circuitry looks like, input output circuitry looks like as far as the data is concerned. Now let me look at the address. I have shown here a counter which is generating, and this could be an enable for this. So this is, let us say, a counter. Again, this need not be a counter, it could be a register, and I could have an address bus and I could have multiple sources to this address bus. My address can also come not just from one source, but it can come from many sources. It doesn't matter. But at any given time, I should enable only one of them. So if you have multiple sources, then you should have an output enable bar to enable this. If you have only one source, it doesn't matter, because that particular address will anyway come to this RAM. Depending upon the type of accesses that you want to do, you may use a counter, you may use a register, you can use multiple, you can use some counters and some registers and so on. And at the time when you want to read or write, you have to select one address from one of the sources. So there will be some decoding and so on used in this. And at the appropriate time, I should generate read and write. Now, the type of control we have studied till now is as a state machine controller. What we have studied is we can generate control signals, we can design a state machine to generate some output signals. Output of a state machine could be the control signals required. Now let us say I want to use this RAM as part of a design where I am generating some inputs and outputs, or I am doing some control operations using the state machine. How do I have a state machine control this RAM? And this is what I am going to discuss now in the next few slides. So reading memory in a state machine, SM here stands for the state machine. Assume that the source for the address is a counter, and I am performing an increment to the counter. Each time I am writing into the next location. Let's say for a very simple case. So my address should be set up. So let us say I am going to perform the read. This is my read cycle. This is my memory read cycle. And this I am going to have to associate with this output of the state. So of course, depending on whether you are using a Moore model or the Milli model, if you are using a Moore model, then you can associate the outputs with the states. If you are using a Milli model, you have to associate with the transitions. So this part is very clear. So now I have to first of all make sure that by the time I perform my read, my address is stable. So at least my counter, if it is let us say an counter, so my counter can be active even at the falling edge, and the output will come a little later after the falling edge. That depends upon the delay of the counter, and that is when my address is going to be stable. If I have multiple sources, I have to enable this address source during this period, and if I am loading the data register here is this RO is my output register, which is a data register. If I am going to load my data register, that I should again do it during this time. So which is the time? So this is the time which is used by the read cycle. So I should have enough time after the address is stable. The address is going to be stable. If you are doing an enable address source, the address will be stable even little later than that. Because after all, if you have a tri-state buffer, that will also have a delay to enable the address onto this. But once the address is stable, so this particular time that is given to this should be sufficient as far as the read cycle time of the memory is concerned. And during this whole phase, the read signal can be high. I have not shown the read signal here, and that's anyway has to be high because I am performing a memory read operation. So I can do that. So basically if you look at it, you can just do it in one clock cycle. As far as the timing for this memory is concerned, there is not much required over here. This is all again related to the address, how the address is generated. This is also related to the enable address source. Only thing is the read has to be high. You can also associate a read signal with this particular edge where it is actually high for this particular duration. I had to load. The only thing I had to remember is I had to load at the falling edge. I had to make sure that I load my data register because after all this is the time that is given for the memory to read. So the whole operation can be done in one clock cycle of or one state of the state machine. So it's a fairly simple way of designing a reading the memory in a state machine is fairly simple. When it comes to writing into the memory in state machine, there are little complications. The complications come essentially because of the fact that the write signal, what is required is the write signal requires to be enclosed completely by the address and data. I am showing here writing memory in a state machine, and I am showing there are 3 states that are required to do this. This is an extremely safe design. Typically one doesn't use this type of a design if one is bothered about the speed. Because now what's happening is if you use the same state machine, after all when you are using a RAM you are also going to perform read sometime and write sometime, and each time you are performing a read you are using 1 clock cycle, and each time you are performing a write you are using 3 clock cycles. Obviously it's not a very, you are not pushing the design to, you are not using all the capacity of the design. So typically designs are done with some more effort, but let's say if you really want to do a safe design and you are not really concerned about the speed of your design, then you can use this. Later on we will see how variations to this can be done. So you have this address, so there are 3 states. So your address is enabled during all the 3 states. So you have enable address, I am talking like a Moore machine and I am associating with the state. If you talk like a Mealy machine, you can actually, you are designing a Mealy machine, you can associate with the transition. There is no problem. It's similar. So during this, all these 3 clock cycles, the address is stable. So whichever address, so let's say you are writing it into location B, the B address is going to come for 3 clock cycles. So sometime after this, 1, 2, 3 for 3 clock cycles. And write is being performed in the middle. Data will also come for 3 clock cycles. The data that you are, so what does this data enable? The data enable corresponds to, if you again consider the diagram that I had before of the circuit example, so the data source for the data is this. So this has to be enabled again for these 3 clock cycles, and write is associated only with the middle transition, middle state or the middle transition. So the write comes only for 1 clock cycle, and now what you see is this write is completely enclosed by both address and data. It's very clear because I am going to have a stable address for 3 clock cycles, I am going to have a stable data for 3 clock cycles, and so there is enough. And these timings obviously will be much larger than the setup and hold times that will be required by the memory because they are full clock cycles. They are of the same order as the, and your cycle time as far as this is concerned, whatever is your write pulse width, that write pulse width, minimum pulse width should be there for your cycle, for your state machine. So this is a type of a design which is, as I said, it's a safe design and will anyway work without much effort because you have ensured that all your timings, all your restrictions are followed very well. But as I said before, many times one doesn't do this type of a design. If you want to actually do a faster design, There are two ways of going about it. One method is unlike other control signals, almost all other control signals can directly come as an output in case of a Moore machine as a decoding of a state, in case of a Mealy machine as an output which decodes the state and the input signal. But for write signal, if you want to use do a write operation in one clock cycle, you will almost always require some more logic. Okay, and let me tell you what is the type of logic. Your address is going to be generated over this period. This is the time, because if the address is, if you are going a one cycle operation, the address that I am going to write is going to be generated over this. Now, I can generate a write pulse by gating this. But problem is, as soon as I start gating with this, I do any type, this is my clock and this is my write. I can do it in one clock cycle, I can always, so now it is not being associated with the state. If it is a Moore, it's output of a state gated with the clock. Please remember this, because, but what will happen is any type of a gating, so if you are taking a clock as an input and putting some gate, whatever is an AND gate or OR gate or NOR gate, whatever, some gate you have, this particular edge will be delayed from this. So this particular edge will actually arrive here. And that's dangerous for the write. Because what will happen over here is, this particular edge is going to maybe not even be encompassed by this address. And what could happen is, so you may actually not be able to satisfy the whole time requirement. Because after all, the data will also be changing in the same manner as the address, because you are only allowing one clock cycle for doing this. So this is one clock cycle write. So you have to engineer this waveform, and there are many ways to doing it. So what you can do is, this clock that you are using over here for your state machine, you actually use a delayed clock. This is your clock and this is your clock dash, and this is the clock that you use for your state machine, and this is the clock, and remember there is a 2 gate delay that is present between them, and this is the clock that you use to generate your write signal. So because this clock is delayed, so this edge relationship will be maintained, and this, when this edge is going, of course the whole time is required are fairly small, it's only a couple of nanoseconds. So you will be able to meet this requirement that this actually changes. So you write at the beginning when you are doing a memory design, you have to bother about this. The other method is, if you don't want to do this type of delay, and or let's say your hold times are larger and this doesn't meet your requirement, there's another method of doing it, which is, so you start from a master clock. This master clock is actually twice the speed of your actual clock that you use for your state machine. So you actually start from a clock which is twice that speed, and you divide it down. So this is your state machine clock, and this is your master clock, and you are going to perform your write operation in one clock cycle of the machine cycle, and now it is fairly easy by gating to generate a pulse like this, which is the write pulse that you use. So now as far as this clock is concerned, you are doing it in one clock cycle, but as far as the, this is the clock which is the source from which you generate this state machine clock. So in relation to that, you are taking 2 clock cycles to do the write. So what I would like to emphasize here is, whenever you do a design with RAMs, you have to bother about the write timing. You have to satisfy the requirement that the address and data should be stable at the time when the write pulse starts, and also at the time when the write pulse ends. Beyond that, how much time it should be stable before and how much time it should be stable after is something that you can control by your design. So that is about the designs with SRAMs. We will very briefly discuss about dynamic RAMs. those of you who will do a course on microprocessor may perhaps look at more of these timings. It's a mistake here, it should have been DRAM. So dynamic RAM device signals. See, typically what happens is if I go back and look at this, if I might look at my static RAM device signals, so 16 kilobyte is still a fairly small size memory from today's point of view. The memory sizes are already going into megabits. So what happens is the number of address lines keeps on increasing. If you're talking of 1 megabit memory, you have 20 address lines that are coming. And today the device cost is, if you're mass producing a device, you take out the technology and the design cost in the initial few months of the product being in the market. Then basically it is the cost revolves around the cost of fabrication, which is fairly small, and the cost of the package. And the cost of the package is directly dependent upon the number of pins you have. So if you really want to produce a low cost device, you have to reduce the number of pins. And memory is one of the most, let's say, just as a one single kind of device is the most commercially most let's say widely used device, because memory is used in almost all systems, and there are few varieties, so also this is very mass produced. So the cost of the device is very important criteria. And when initially people were making static RAM based devices, so when they went to dynamic RAM, of course DRAM has another advantage, we will talk about that, that's why DRAM is preferred. But when people want to DRAM, they also want to make low cost devices, so what they wanted was the number of pins should be reduced. And the way the number of pins can be reduced is by using multiplexing. You do not supply all the address inputs at one go, but you supply the address in two parts. If you consider your memory, you can consider them to be instead of considering them to be a linear array, you can consider it to be a two-dimensional array, where you have a row and a column, and which determines the bit. If it of course a multi-bit memory, if it's 8 bits or so, then you can consider them to be 8 layers. Okay, that's not difficult to think of, whatever the number of bits. So if you are considering, let's say we are talking of a 1 bit or even 4 bits, so the 4 bits means data out will be 4 bits, data in will be 4 bits. But the address lines themselves are not, all of them do not come simultaneously, but they come in two stages, row address and column address. And remember, when we discussed coincident decoding, we anyway discussed this issue that it's easier to decode if you are actually dividing your address lines into two parts, because you can do your decoder delays will be smaller. So there is something called a row address strobe, and there is something called a column address strobe, and they define when the row address is coming and when the column address is coming. These are row address and column address. As far as the other two control signals are concerned, they are similar to the way we consider static RAM. Once I discuss the timing, I will also say that why DRAMs are extremely popular and low cost, but let me talk about that later. First, let me just show you the timing of this. So now you have these additional signals, and these additional signals, how are the timing of these signals are related. I am showing again a bus cycle, a memory cycle. Let us say it is a read cycle and it is a write cycle. I am not shown here the read and write signal, but the read and write signal will follow the similar logic as in case of the dynamic, in the case of the static RAM. Your write signal will come somewhere over here. You will have this and you will have your write signal somewhere. Actually after this. So this will be your read write signal. But more important is this, let's say important difference is that you have this row address strobe and column address strobe. And what happens over here is this is your row address that is coming. This is the row address A. This is your column address A, row address B, column address B. And along with this row address, the row address strobe comes, and you will be internally be latching this address somewhere. So there will be a latch inside or a register inside which will actually latch this. Of course, what is the timing relationship, whether it is an edge trigger, level trigger, that differ in the type of dynamic RAM you have. Of course, this address latch is going to be only one. We are not going to duplicate it. Even if it's a 1 megabit DRAM, I will have only 1 bit register at the input, which could be level or edge trigger. So So this is the time when the row address comes and row address gets latched, and then the column address comes and column address gets latched, and during this time when the column address is coming, you perform your read or write operation. Because complete address has come, row and column, and you perform the read. If you are doing a read, you do it during this time, and if you are doing a write, you do it during this time. And the idea of doing this is essentially only to save the number of pins that you have in your memory device. Because now I need not have separate pins, so I need only half the number of pins. So if it is a 1 megabit device, I only require 10 address lines. And the same 10 address lines, I have to supply first the row address and then I have to supply the column address. As far as the usage of this device concerns, it's become a little more complicated because you have to go through this sequence. If you consider in terms of a state machine driving it, then state machine has to first generate this row address, then it has to generate signals for this column address. It also has to select the appropriate register. There could be one register or counter which may be generating the row address and another register or counter which may be generating the column address. And on the same address bus, you have to enable them alternatively. During the row address time, I have to enable this register, and during the column address, I have to enable this register. And in this way, it is possible that I can interface this. Okay, now a last comment about the why dynamic RAM at all. The dynamic RAMs are more complex devices to use, but as far as the design is concerned, they are much cheaper than static RAM. Fundamentally, in case of a static RAM, you have a flip-flop. SRAM is based around flip-flops. It's some type of a flip-flop which is going to hold the fact that whether that particular cell contains 0 or 1. In case of a DRAM, it is not the flip-flop which holds, it is the capacitor which holds the fact that, and this capacitor is not something that you need to put in. A capacitor comes as a stay capacitance on any device that you make. So you basically, a DRAM is, for one cell you require only one transistor, and this transistor, I will explain to you how this transistor works. And whereas in case of a SRAM, the minimum cells that have been made with SRAM are 3, but more often 4. Okay. So the SRAM cells require 3 or 4 transistors. So what happens is, or actually some of them are even more complex depending upon number of issues, the speeds and so on that comes in. So as far as the technology is concerned, because you are limited by how many transistors you can fabricate in a particular area of silicon, so you can always get DRAMs which are 2 to 4 times capacity, higher capacity than SRAMs in terms of the capacity. So at any time you have 1 megabit SRAM, possibly you may have a 4 megabit DRAM possibly, which essentially means that the cost per unit of storage is much cheaper in DRAM than SRAM. That's why typically all low cost products like PCs and so on and so forth, they tend to use DRAMs, because where the cost is a criteria, you can make much higher capacity memory in the same silicon area. And there is also a technology driver. At any given time, the technology is determined by, one of the good measures of technology is what is the capacity of the DRAM that we are producing in a given area of silicon. The way the DRAM works is, of course, I have only shown you the circuitry for reading and writing. DRAM also requires refresh, because the charge, actually the particular cell, whether it is 1 or a 0, is stored in a capacitor, and any capacitor is going to have a leakage path. There will be a path by which this capacitor can discharge or charge. So one important factor about DRAMs is that if you have stored a particular value in a cell and you do not refresh it for a considerable period of time, the value that you read afterwards may be wrong. You may have stored a 1 and the capacitor may have discharged and you may be reading a 0, or vice versa. So it requires a regular refresh. Of course, how much refresh it requires depends upon your design, like how often you need to refresh. But interestingly, a lot of DRAM circuitry today is made in such a manner that if you actually access even one location in a block, the whole block will be automatically refreshed. The circuitry is built within the DRAM itself. So as far as the user is concerned, it may be hidden from it, the refresh may be hidden, but a user may be forced to actually access at least one location in a certain block. So there are variations to this, considerable variations to this, but refresh is an important part, and only then the DRAM works properly, that if you are refreshing the cell which actually holds the data. With this we will end today's lecture, and we will have a